Hello, today we are going to talk about the topic that is very important, that is isotopes. So, isotopes are the atoms that are from same element, but they have different number of neutrons and different mass number, although they have the same number of protons. So, simple definition of isotope is isotopes are the atom of the same element with same atomic number but different mass number. Why are they same element? The identity of element depends on its number of protons. Okay, so that is atomic number. So atomic number is same. Since isotopes have same number of proton, they are the same element. For example, there are example of two isotopes, carbon 12 and carbon 14. So you can see here the carbon 12 has 6 proton, whereas carbon 14 also has a 6 protons. The difference is number of neutrons in isotopes. Here the number of neutrons are 6. For carbon 14, that number of neutron is 8. Both carbon, because they both have 6 protons. So structure of isotope. This is an example for carbon. Carbon has 6 proton, carbon 12, sorry, has 6 neutrons, 6 electrons, and the mass number is 12. Now, carbon 13. It has the same number of protons, but now number of neutrons are 7. So, atomic mass number is simply we add proton and neutron. So, 6 plus 7 is 13. Mass number now is different from carbon 12. That is same for cobalt. Cobalt has exact same number of protons, but number of neutrons, one more neutron has been increased. So number of electrons will remain the same if it is not charged particle. Negative or positive, that's a different story. Now you can see 6 plus 8 is now 14, so mass number is now 14. Okay, mass number is simply is equal to proton plus neutron, we have done in the last lecture as well. So neutron is equal to mass number minus atomic number. For example of isotopes, carbon 12, 13, 14, atomic number is 6, whereas mass number is 12, 13, and 14. So now first, what is the isotopes of hydrogen? Hydrogen 1 has, its name is Protium. It has one proton, but there has been no neutron. Hydrogen 2 is called Deuterium, and it has one proton and one neutron. Whereas hydrogen 3, we called it Tritium, and it has one proton and two neutrons. Now we are going to do the example of chlorine. That is chlorine 35 and that is chlorine 37. We know that they both have 17 proton and 17 electron. If it's a neutral atom, then electron and proton number are the same. The difference is in the neutrons. So 35 minus 17 is 18. So chlorine 35 has 18 neutron, whereas chlorine 37 has 20. 37 minus 17, we have to subtract it by this value, this proton number. We also subtract this from this proton number, so they both are different. Properties of isotopes. Chemical properties, they are almost identical. Because why? Because they have the same number of electrons, so they react the same way as the other isotope. Physical properties, yes, they are different. Okay, they are not the same. They have different mass, different densities, and the due to this, they have different melting and boiling points slightly. There are two types of isotopes. One is radioactive and other one is stable isotopes. What is stable isotopes? They don't emit radiation. For example, carbon 12, 13, oxygen 16. They don't emit radiation. Okay, whereas radioactive isotopes have a unstable nuclei. They emit radiation to become more stable. That is an important thing. Okay, and example of them is carbon 14 is a radioactive element. Uranium that we use for nuclear reaction. It is used for a generation of electricity as well as for military purposes. They emit radiation. Cobalt 60, yes, they also cobalt 60 also emit radiation. So why we need isotopes? Isotopes are used for different reasons. For example, carbon 14 is used for dating fossil fuel and archaeological remains. If you want to uh, mm, measure the date of the fossil fuel, for example, maybe it's 1 million year ago that thing went into the earth, so we use carbon 14 to predict the date. Cobalt 16 for cancer radiotherapy. Iodine 131 diagnosing and treating thyroid disorder. Technetium 99 medical imaging for scan. And uranium 235 for nuclear power generation. That's all about it.